Okay, so a quick reminder before we start to discuss graph theory. Okay, so next week we're going to have some paper presentations. So make sure that if you want to present your paper next week, register your paper on the Google Sheet. Okay, so because I think already we have like 6 paper registrations. So this means we have still like 3 students or more who haven't registered their paper yet. Okay, so yeah, once you find your paper, just register your paper on the Google Sheet. And also you can find your update score of your midterm on Moodle. Okay, so if you have any question regarding the score, you can reach out to the TA. All right, so back to graph theory. So last week we discussed we basically discussed 4 different problems, namely independent set, vertex cover. So these 2 problems are related to vertices, okay? And we have these 2 problems related to edges, okay? So matchings and edge cover. So the reason that we discuss these 4 problems is that I want to show that these problems, they have some spatial relationship, okay? In particular, when we discuss matchings, we say that we can use vertex cover as an upper bound for matchings. And when we discuss independent set, we say that, okay, we can now use edge cover as an upper bound for independent set, okay? But I haven't explained how to discover this upper bound. So given, say, maximum matching, how did I know that I should look at the vertex cover problem? And when we discuss independent set, how did I discover that edge cover is a proper upper bound? Okay, so today we're going to discuss how to find this upper bound and lower bound. So in particular, given a problem, today I'm going to show you a systematic way to to find upper bounds, okay, or lower bounds, depending on the problem. Whether it's a maximization problem like independent set, then we want to have an upper bound. And if it's a minimization problem like vertex cover, we want to pick as few as possible vertices as possible. So in this case, for minimization problem, we want to find lower bound. Okay, so let's begin with example. So the example that I'm going to show you is not a graph theory problem, okay? But later I'm going to show you the relationship between the problem that I gave you and graph theory. So this is a maximization problem. Probably you're going to see when you're studied high school, okay? So you have this objective function, and you have 2 variables, x1 and x2. So these are your 2 variables. And you have some constraints. Okay. So your goal is to find a proper setting of x1 and x2. So you want to find some values for x1 and x2 so that you can increase or maximize x1 plus 6x2. So this is your goal, okay? But you have some constraint. So x1 cannot be greater than 200. x2 cannot be greater than 300. And their sum is at most 400. Okay? So under these constraints, you want to maximize this sum. Okay? Okay, so given this problem, let's try a few possible solutions and see whether these solutions give you the best answers. So let's first consider the first constraint. So here we have 3 constraints. So normally the last one is this non-negativity constraint. So in the following discussion, we mainly consider the first 3 constraints. Okay. All right. So let's first consider constraint 1. So constraint 1 says that x1 is at most 200. And since we want to maximize this term, I think it makes sense to set x1 to 200. Okay? So let's just set x1 to 200. Okay? Now, if x1 is set to 200, then what is the highest possible value for x2? So x2, well, there are 2 constraints. So x2 is at most 300, so probably you will say that x2 should be set to 300. But then it violates the third constraint, because the third constraint says that their sum is at most 400. So basically, once you set x1 to 200, then you have to follow the third constraint, which says that their sum is at most 400. And this will give you x2 is 200. Okay? All right, so we said that this is a feasible solution, okay? Because it satisfies every constraint here, okay? All right, so, but this is our goal, so let's check, let's count, okay? So x1 plus 6x2. So in this case, this will be 1400. Okay. So this is our first guess. Okay, and this is a reasonable guess because it's like we maximize x1 first, and then we try to maximize x2. Okay. So that's the first one, and the second one is now let's perhaps maximize x2. Right? So x2 let's set x2 to 300. Okay? Now, once you set x2 to 300, now you have 2 constraints to consider. So the first one and the third one. So I think you cannot follow the first one because if you set x1 to 200, then their sum would exceed 400. So in this case, x1 is at most 100. Okay. So once again, you can check. Okay, so this is also a feasible solution because first x1 is less than 200, x2 is equal to 300, and their sum is equal to 400. Okay, so this solution satisfies every constraint. Therefore, it is a feasible solution. All right. So now let's check the objective value. Okay. So this time, the objective value will be 1900. Okay. And since we want to maximize this sum, so clearly we should choose this one instead of the first solution, okay? Because this yields a higher objective value. Okay. Now, we've come to a point, it's like when we solve max-bound matching and when we have a matching and want to see whether this is the best, okay? Want to have some proof or some certificate to show that this is indeed the best solution, okay? So in this case, you may think, okay, is it possible to find a better solution? A solution that can reach, for example, like 2,000. Okay. So next I'm going to show you that this is impossible by giving you some certificate, okay? And so the idea is to construct some upper bound, okay? So when we discuss matching, the upper bound we use is vertex cover. So in this case, we're going to use a general technique to derive the upper bound. So the idea is that I'm going to find some weighted combination of these three constraints, okay? So let me show you some example, okay? Okay. So let's combine the first two constraints. Okay, and when we combine these two constraints, I'm going to multiply the second constraint by 6. Okay. So this operation is like, first I have one copy of the first constraint. And then I have 6 copies of the second constraint. Okay. So the sum will be $2,000. Okay. So because what I did here is I just manipulate the constraints here. So this will be an upper bound. Okay. So based on this operation, I know that it's impossible to have a solution that is greater than 2,000. Okay. Because if you have some solution that is greater than 2,000, it will violate some of these two constraints here. Okay. So this is what we're going to do today. So the mission or the goal today is to find some weighted combination of the constraints. So here the weight is 1 for constraint number 1 and 6 for constraint number 2, okay? And I want to find some proper weights for these constraints, okay? So this is just one possible weights, okay? So let's consider a different way of assigning weights. Okay. So in this weighted combination, we haven't used the third constraint. So let's try to use this third constraint. Okay. Okay. So Well, because the coefficient of x1 is 1 here, so it makes sense to just assign a weight of 1 to the third constant, because if you say assign a weight of 2, then you'll get 2x1 plus 2x2. So this will becomes 2x1, which is greater than x1, so they don't match. Okay, so we want to match exactly the coefficients here. Okay, so we're going to just have one copy of the third constraint. Okay. Now, if I have one copy of the first constraint or of the third constraint, then I still have to add some x2 because the coefficient of x2 is 6. But now I only have 1 for x2 because this is 1 times the third constraint. So now in my weighted combination here, the coefficient of x2 is just 1. Okay? So to fix this, I can add 5 copies of constraint 2. Okay. So let's find out the combination. So I have x1 plus x2. So this is almost 400. And then I have 5 copies of constraint 2. So this will give 5x2 is almost 1500. Okay? And then I just add these 2 constraints. Okay? All right, so by combining this constraint 2 and constraint 3, I get this. Well, this is an upper bound. So this upper bound says no matter how you assign x1, x2, as long as you have to satisfy 2 and 3, x1 plus x2 is at most 1900. So if your objective function, if you want to maximize x1 plus x2, x1 plus 6x2, the best you can do is 1900. Okay? So now we've already have a solution of 1900. So this matches the upper bound here. So this is like a certificate or a proof that shows 1900 is indeed the best. Okay? You cannot find a better solution because you have constraint 2 and 3. Okay? OK， 所以刚刚我们做的事情其实说穿了很简单，就是我们要找到这些 constraint 的组合，而且这个组合我可以在把它们加起来之前乘上一些系数。像这个例子的话，我们在限制是2这边是乘上5 ，OK， 然后限制3就没有变 ，OK， 就乘上1这样子。然后我们会把这些限制是做完，就是乘上一些倍数之后再加起来。那我们希望说，透过这个方法去兜出最一开始我们的目标的上限。OK。那这边我们刚刚就看到2种这种加权的组合的方法。所以第一种是限制是1就1倍，然后限制是2是6倍，这是一种。然后这里呢，我们会看到它告诉我们的事情是 x1 加6x2 是最多是2000 ，OK， 所以这个它已经就告诉我们说，不管你怎么设定，它的 solution 最多就是到2000 ，OK， 你不可能找到一个比如说2100的，不可能。但是你会看到我们刚刚这个 solution 是1900，因为1900跟2000还是有个 gap， 所以当你看到这个 upper bound 的时候，你心中还是会想说 ，OK， 有没有可能有一个 solution 它算出来是1903之类的 ，OK？ 因为这个还是符合这个得到的 upper bound，OK？、所以呢，我们刚刚又去看了第二个去组合这些 constraint 的方式 ，OK？ 那这边呢，这个 constraint 的系数就不太一样，更明确来讲，我们刚刚那个都没有用到第三个限制式，那这边有用到第三个限制式 ，OK？ 然后这边就没有用到第一个限制式 ，OK？ 所以我们这边的组合做出来之后，哎，就是1900，那这个1900刚好就会跟我们刚刚这个 solution 是有互相搭配，就是简单说是一样 ，OK？ 所以这一个下面这个weighted combination 就某种程度就证明了上面这个1900就是最好的 solution。你不可能找到一个其他的 feasible solution， 它可以满足它可以超过1900，不可能，因为它都要满足3跟2。OK， 所以到这里有问题吗？我知道到这边目前为止，可能跟 graph theory 大家可能完全看不出来关系在哪，大家等一下大家就会知道。有问题吗？都清楚 ？OK。Okay, so so this is like the general idea to find upper bound, okay? But now the question is, you see, we don't know how to find these weights, okay? And these weights matter because you have to find a proper set of weights in order to establish a good bound or a tight bound that matches your solution, okay? So finding these weights is important, and but it's not easy, okay? There's no efficient or no clear way of how to find these bounds or how to find these weights. So instead of designing an algorithm to find these weights, we'll first model this problem, model this weight finding procedure as a problem, okay? So So to model this as a problem, we're going to treat these weights, like 1 and 5 here, or 1 and 6 here. I'm going to treat this as variables. And I want to find some proper settings for these variables, okay? And you see, if I treat these weights as variables, then it's like I have two solutions. So the first solution is 1, 6, and this gives us 2,000. And the second solution, once again, if I treat this 1 and 5 as variable, then this is a solution that gives us 1,900. Okay, and we all know that 1,900 is better than 2,000 because I want to have a tight bound. I want to minimize this term, okay? I want to minimize it, and hopefully the result I get matches the solution here, okay? But the general idea is that I want to minimize, okay? Okay, so this is the first step to realize that the problem that we're going to solve is like a minimization problem. We want to minimize this, okay? And what is this, okay? So this is like the sum of the right-hand side, because now we have some constraints, and we only consider the right-hand side, okay? And we want to find the sum of the right-hand side, and want to minimize the sum of right-hand side, okay? And by giving different weights to different constraints, I can adjust the right-hand side here, okay? So for example, the first solution gives us 2 and 1800 for the right-hand side, okay? And the second solution gives us 4 and 1500 on the right-hand side, okay? So by adjusting the weights, which now we viewed as variables now, we can adjust the right-hand side, okay? So let me first copy. Okay. Okay, so we have 3 constraints, and we have 3 right-hand side. And then we want to find some variables which will be used as like a weight, which will be multiplied to the right-hand side. And then we want to minimize the sum of the right-hand side, okay? Okay, so because we want to treat these weights as variables, so I'm going to use y1, y2, and y3. So this will be the weights, okay? So y1 is the weight for constraint 1, y2 will be the weight for constraint 2, and y3 will be the weight for constraint 3, okay? Okay, so taking this solution as an example, then this solution corresponds to this 0, 5, 1, because in this weighted combination, we didn't consider constraint 1, which means the coefficient or the weight for constraint 1 is just 0, okay? And the weight of constraint 2 is 5, okay? And the weight for constraint 3 is 1. So for this solution, using the notation we have here, okay? So y1, y2, y3 corresponds to the weights. And this solution is like y1, y2, y3 equals 0, 5, 1, okay? So similarly, this is like okay, 1, 6, 0. Okay. Okay. So let's just multiply y1 into constraint 1, y2 into constraint 2, y3 into constraint 3, and find the weighted combination. So okay, so this one is the first constraint times y1, okay? So you can see that both the left-hand side and the right-hand side it's multiplied by y1, okay? Okay, so this is the result we get by multiplying y2 to constraint 2. Okay. All right, so the last constraint is the same, okay? We just multiply the right-hand side and left-hand side by y3, okay? So we get y3x1 plus y3x2 is at most 400 times y3, okay? And then we have to find the weighted combination, okay? So what we did here is actually like a general version of the previous examples. Okay, in this example, we set y1, y2, y3 to this exact setting, and we get this exact weighted combination. Okay. Now the procedure is the same. I just replace these specific numbers with these variables y1, y2, and y3. Okay, but the logic is the same. Okay. Okay. So once again, I didn't add any new idea, except that now I use y1, y2, and y3 as the weights. Okay. And yeah, the general idea is the same. Okay. So if you replace y1, y2, y3 with 0, 5, 1, then this equality will be x1 plus 6x2 is at most 1900. Okay. For example, you can try. Okay. So y1, y2, y3. Okay, so you plug in 0, 5, 1 into this, you get y1 plus y3, 1, okay? Because y1 is 1, y1 is 0, y3 is 1, okay? So you get x1 plus 6x2 is at most 200 times what y1 is 0, so this one cancels out. And this becomes, let's write it down, okay? Okay. So the right hand side is 1900. So really nothing new here, okay? The only difference is now I use some y1, y2, y3 to represent the weights.有问题吗？所以跟前面的讨论基本上是一样的，唯一的差别就是我刚刚说的 y1, y2, y3 现在要变成是这个每一个限制式的 倍数 ，OK， 就是我要把它加起来之前，就要先乘上的倍数。到目前为止有任何不清楚的地方吗？都清楚 ，OK。Okay. Now let's like model the process of finding these weights as an optimization problem. And because we want to have this right-hand side as small as possible, so this is a minimization problem. And the goal is to minimize this, okay? Okay? So this is our goal, okay? We want to find y1, y2, and y3 so that this can be minimized, okay? Then you can say, well, why not just set y1, y2, y3 to 0, then you get 0. This is like a very good low upper bound, okay? But you have to satisfy some constraint. So the constraint is that when you look at the left-hand side, okay, at least it should be like, matches the objective function in the original problem, okay? So if the original problem is to maximize x1 plus 6x2, then I want to find some upper bounds related to this, okay? So in this solution, the result is that the left-hand side is exactly x1 plus 6x2, okay? So similarly, for the first weight, the left-hand side gives us exactly the same form of the objective function, okay? So x1 plus 6x2. So in other words, we have to make sure that this weighted combination is an upper bound, okay? The left-hand side is an upper bound of the original function. So this one should be an upper bound. Oops. Okay. All right, so to make this an upper bound for x1 plus 6x2, we have to make sure that the coefficient of x1, that is y1 plus y3, is at least 1, okay? And the coefficient of x2, that is y2 plus y3, is at least 6. Okay, so this y1 plus y3 comes from this, okay? So this is the coefficient of x1 in the weighted combination that we get, okay? And this y2 plus y3 is from here, okay? The coefficient of x2 in our weighted combination, okay? Okay, so intuitively, this is to find small upper bound. And this is to make sure that the weighted combination is an upper bound. Okay. And finally, we have to add the non-negative constraint. Okay, so all these weights, they must be positive, okay, or zero, okay. So can you see why we cannot have like negative weights? What happens if some of these weights is negative? 如果这个里面有一些 y1 之类的或 y2 whatever， 如果有一些 weight 是负的数字，那会发生什么事？有人可以看得出来？ It has something to do with the sign here. So in the original problem, this is less than or equal to sign, okay? And the reason that we can keep this less than or equal to sign is because the weight we apply to both sides is a positive weight. If it's a negative number, then we should change the sign from less than to equal to, less than equal to, less than or equal to greater than or equal to. So we have to flip the sign here if the weight is negative. Okay? So that's why we have to make sure that the weights are positive or zero. Okay? 所以最后一个刚刚加上去的，就是要确保说我们这个权重都是正，它不能是负，因为如果是负数的话，我们刚刚在把这个权重乘到这个不等式的两边的时候，这个不等式的符号就会改变，从小于等于变成大于等于。所以那如果它改变之后，它就很明显就没办法直接加起来。OK。Okay, so this is the problem. So this is a problem that we use to find the proper weights, okay? So by proper, I mean, first of all, you have to make sure that the weighted combination is an upper bound, okay? So this is why we have these constraints here. And we also want to find the base, the smallest upper bound. So we have this objective function here, okay? Okay, so in this slide, we actually have two problems. So this is the first problem. And okay, so this is the green one is the first problem, the original problem, and the yellow one is the new problem that we use to find weights. Okay, so you see, in some sense, we transform the original problem into a new problem. Okay, so it's similar to the process where we transform matching into vertex cover. So we have some problem transformation. And for this kind of transformation, we say this is, so the original problem is the primal problem. And the new problem is called the dual problem. Okay. And this problem transformation is called primal dual transformation. Okay? Because it transformed the original primal problem into a new dual problem. Okay? And the purpose of this dual problem is to give you some upper bound. Okay? Okay, so let's take a break, and I think I can give you more examples, okay? And then I'll show you why matching and vertex cover, these two problems fit into this transformation, okay? So in particular, I'm going to show you that when the primal problem is matching and you do this transformation, you get vertex cover, okay? And when the primal problem is independent set, and you do this transformation, you get edge cover, okay? So that's the reason that we can get vertex cover and edge cover when we discuss matching and independent set, okay? Okay, so let's take a break, okay? All right, so let's try another example, okay? So this time we have 3 variables, x1, x2, and x3, and we have 4 constraints, okay? And we want to apply the same procedure to, now the goal is not to find the optimal solution for this problem. The goal is to construct the dual problem, okay? That's the whole point of this discussion, okay? So the goal is to find the objective function for the dual problem. The goal is to find the constraints for the dual problem and the variables, okay? Good. So the first step is always to create these y1, y2, y3 variables because now we want to assign weights, okay? And because we have 4 constraints, okay? 1, 2, 3, 4. So we have to create 4 variables. y1, y2, y3, and y4, okay? And by the way, these variables, they are called dual variables. Okay. Okay. So basically, we just have to find the weighted combination of these constraints, and then we can get the object function and the constraints. Okay. But now, before we construct the weighted combination, observe that some of the constraints here, in particular this one, looks weird, right? Because all the other constraints, they are less than or equal to, okay? But this one is greater than or equal to, okay? And so before we combine these constraints, we have to make sure that they all have the same sign, okay? And because this is a maximization problem, and we want to find some upper bound. So whenever you consider upper bound, you should think of less than or equal to, because naturally, less than or equal to gives you upper bound, okay? If it's less than or equal to 300, it simply says that the upper bound for this is 300. So whenever you want to construct upper bound, you have to make sure that the sign is less than or equal to, okay? So we have to first adjust the sign here, okay? And how to adjust the sign here? We just multiply -1 to both sides. So okay. So now every sign here is a less than or equal to sign. And then we can find the weighted combination. Okay. Okay. So this time, I think now we all know the purpose of finding this weighted combination is to find the coefficient of x1, the coefficient of x2, and if we have x3, we also have to find the coefficient of x3. And the reason that we want to find this coefficient is because we want to make sure that this weighted combination gives an upper bound. So for example, here we need to make sure that y1 plus y3 is at least 1, and y2 plus y3 is at least 6. Okay? So that's the reason we want to find this weighted combination. So what matters here is the coefficient of x1 and the coefficient of x2, okay? And also we have to figure out the objective function. And what's the objective function here? It's just okay, it's just the sum of the right-hand side, okay? Because we want to have the smallest possible upper bound, okay? So we want to minimize this, okay? So with this in mind, we can just try to construct the dual problem. Okay. So let's start with the objective function. Okay. So the objective function is from the right-hand side of the weighted combination. So I'm going to just write it down. Okay. So this will be, sorry, not this slide. The right-hand side of the weighted combination will be 300 y1 plus 1000 y2 plus negative 500 y3 plus 400 y4. Okay? So 300 y1 plus 1000 y2 minus 500 y3 plus 400 y4. Okay? So if you really write down all the weighted combination here, this will be your right-hand side. Okay? Because the right-hand side is simple. It's just you just multiply the right-hand side of each constant here by the dual variable y1, y2, y3, y4 here. Okay? 所以第一步去建这种 dual problem， 你可以从这个它的目标就 objective function 开始。所以第一个，这个是一个 minimization 的问题 ，OK？ 所以我们要找到越小的 upper bound 越好 ，OK？ 所以是 minimization。然后我们的目标呢，就是回忆我们刚刚的，我们刚刚都是不断的想要去减少，从譬如说刚刚的前面例子里面，我们是本来的 right hand side 是2000，然后我们把它减少到1900 ，OK？ 那所以我们目标都是希望这个 right hand side 越小越好。那这 right hand side 怎么得到的？其实就是这些限制式的右边再乘上你的 weight，OK？ 所以这边限制式的右边再乘上 weight， 就会是我们的目标。我们希望这个越小越好。Okay. All right. So next, the constraint. Okay. So the purpose of the constraint is to make sure the weighted combination is an upper bound. Okay. In particular, for this example, we have to make sure that in the weighted combination, the coefficient of x1 should be at least 2. And the coefficient of x2 should be at least 3. And the coefficient of x3 should be at least -4. Okay? All right, so let's first consider what's the coefficient of x1. Okay? So the coefficient of x1 in the weighted combination will be, well, first of all, you get 6y1, right? Because you're going to multiply y1 to both sides of the first constraint. So the coefficient of x1 will become 6y1. Okay? And we want to make sure that this is at least 2. And the coefficient of x2 should be at least 3. And the coefficient of x3 should be at least -4. Okay? Okay, so we haven't finished here, okay? Because the coefficient of x1 also includes this term, which becomes y2 times 1, okay? Okay. And for the third constraint, because it does not involve x1, so you don't have to consider this. And the fourth, the coefficient on the right hand side, on the left hand side is 1. So 1 times y4, okay? Okay, so in the weighted combination, the coefficient of x1 is 6y1 plus y2 plus y4. Okay, so let's for x1 now, let's consider x2. So we know that the coefficient of x2 should be at least 3, okay? And what's the coefficient of x2? So here you get 1 times y1. And from the second constraint, you get 1 times y2. And from the third constraint, you get y3 times -1. So it's minus y3. Okay? Okay, and last constraint does not involve x2. So that's it. So the coefficient of x2 is just y1 plus y2 minus y3. Okay. Okay, so last, the coefficient of x3. So the first one does not involve x3, so let's consider the second constraint. So from the second constraint, the coefficient of x3 is 1. So multiply by y2, you get y2 here, and 4 y3. So plus 4 y3 and plus 3 y4. Okay. And finally, all these dual variables, they cannot be negative. Okay, so at least 0. Okay, so this is your dual problem. Okay.有问题吗？有不清楚哪一步为什么要这样做的吗？有不希望你会需要去背这些东西，因为它都是有原因的，所以如果你不知道原因的话，就应该要提出来。可能我哪里没有讲清楚。所以重点基本上有几个，第一个就是你要 dual variable， 因为这些就会是它的 weight， 然后你会有目标，因为你想要用越小的 upper bound 越好 ，OK， 所以你会有这个目标，然后这个目标就是我们把这些 y1 这些当做权重乘进去兜出来的东西的右边 ，OK， 就是这里，你希望这个右边的这个总和会越小越好，那这样你才可以拿到最小的那个 upper bound。然后再来就是这些限制式，就是要确保说你最后兜出来的东西，它会是本来的目标的 upper bound，OK，所以 x1 它的上限应该要是至少是2，x1 的系数至少要是2，x2 的系数至少要是3，以此类推。有不清楚、不合理的地方吗 ？OK。Okay. So now let's consider matching. Okay. maximum matching, to be precise. Okay, so let's consider this bipolar graph and want to find the maximum matching. Okay, so we have 7 edges, okay? And we have 6 vertices. So in order to apply the previous primordial transformation, we have to first model this maximum matching problem as a problem in this form, where we have some objective function, we have some variables, and we have some constraints, okay? All right, so first we have to create the variables. So what should be the variables for this maximum matching problem?所以在前面的那些问题的讨论里面，基本上有几个元素。第一个，你的变数，你的 variable 是什么？然后第二个，你的目标是什么？然后第三个，你的限制是什么 ？OK。And all the constraints, they have the same form. The form is that it's a simple linear inequality. Okay, so the left-hand side is just some linear or weighted combination of the variable, and the right-hand side is just some constant. Okay, so you cannot have some very complex constraints, say like for example x1 squared plus the square root of x2 plus log x3. No, you cannot have those. Okay, all you can do is to find a weighted combination. Okay. Okay, so for this problem, because we have to determine whether for every edge we have to determine whether it's in the matching or not. Okay, because we have to choose edges. Okay, so we will create a variable for every edge. Okay, indicating whether it's chosen in the matching or not. Okay, so for H, E, I, we create a variable xi. Okay. So the physical meaning is that. So it's first of all, it's a binary variable. Okay. I know that in the previous examples we do not have binary variables, but trust me, it didn't change anything. Okay, so yeah, xi is a binary variable. So when xi is 0, this means ei is not in the matching. And when xi is 1, this means ei is chosen. Okay, so it's in the matching. So that's our variable. Okay. So because we have 7 edges, E1 to E7, then we have 7 variables, x1 to x7. Okay, so that's our variables. All right, so what's the objective function? Okay. So because this is a maximization problem, so it's max, okay? So max something, okay? So what should be the constraint? Oh, sorry, the objective function here. So what's the goal of maximum matching? Right, it's just the sum of all the variables. Okay? Right, because if xi is 1, this means ei is chosen. All right, and if it's 0, this means it does not, it's not in the matching. So by computing the sum of all the variables, you get the number of edges in the matching, okay? So this is the number of edges in the matching, okay? And because we want to have the maximum matching, we want to maximize the number of edges in the matching, okay? So that's our goal, that's our objective function. Okay, so next, the constraints. Okay, so without the constraint, you can just say x1 is 1, x2 is 1, all the variables here are 1, okay, if there are no constraints, okay? But there are some constraints. So because in a matching, edges cannot share endpoints, okay? They cannot touch, okay? So we have to make sure that these edges in the matching, they do not share endpoints. So how to use inequality to model these constraints? Because I just said that the constraint should be in a very simple form of linear or weighted combination. So you cannot say that E1, E2, you can choose at most 1, or E5, E6, E7, you can choose at most 1. No, you cannot use English or natural language to model the constraint. You have to use inequality, linear inequality to represent the constraint. So what should be the constraint? So let's consider E1 and E2, okay? So we know that between E1 and E2, we can choose at most one of them, okay? So how to use an equality to model this constraint?
I think we can create a constraint for every vertex.
Mm-hmm.
Like for example, for B1, the edge touch B1 is B1 and B2. So we can create a constraint that is x1 plus x2. Is less or equal to 1.
Exactly, okay? So let's consider this one, okay? So x1 plus x2 is at most 1. So this combined with our definition of xi, so this immediately tells us that at most one of them can be set to 1. Okay, you cannot have both variables being set to 1. This will violate this constraint, okay? So the physical meaning of this inequality is that we can choose at most one of the edges in E1 or E2, okay? So that's how we deal with V1 to make sure that all the edges incident to V1. From these edges, we can choose at most one edge. Okay, so that's for V1. And similarly for V2. So we have to create a constraint, making sure that E3 and E4, among these two edges, we can choose at most one. Okay, so following the same idea, we get x3 plus x4 is at most 1. Okay? So similarly for V3. But now V3 has 3 edges. So x5 plus x6 plus x7 is at most 1. Okay? So among these 3 edges, we can choose at most 1. Okay, for V4, edges incident to V4 are E1, E3, and E5. So x1 plus x3 plus x5 is at most 1. Okay. And for V5, it's x2 plus x6 is at most 1. Okay, and finally E4 and E7. So x4 plus x7 is at most 1. Okay. All right. So these constraints, they are created in a way that for every vertex, we want to make sure that at most one of the incident edges is chosen. Okay? So to do this, we just consider the sum of the variables correspond to the incident edges and make sure that their sum is at most 1. Okay? So because we have this limitation or definition of xi, saying that if xi is 0, this means this corresponding edge is not in a matching, and if it's 1, then it's in a matching. So combining this definition and the constraint, we get the constraint we like. Okay. Okay, so this is maximum matching, okay? And then we can apply the dual or primal dual transformation, okay? Okay, so the first step for this primal dual transformation is always to create the variables, the dual variables. And we have one dual variable, that is weight, for every constraint here. So because we have 6 constraints, so we have 6 dual variables. Y1, Y2, Y3, Y4, Y5, and Y6. Okay. Okay, so the dual problem is always a minimization problem because we want to find the smallest upper bound. Okay, so it's min. And then we have to figure out the objective function, which is just like the product of the right-hand side of the constraint and the dual variables. So the product of these two is just y1 plus y2 okay, so it's just the sum of all the variables. Okay, and observe that the reason we have this constraint is that for every vertex, we have to make sure that at most one of its instant edges is chosen. So it's like we create one dual variable for every vertex. Okay? So I'm going to write down y1, y2, y3. I'm going to write out these dual variables alongside the vertexes. Okay. Okay. Now let's consider the coefficient. The constraint, which corresponds to the coefficient of the original problem. Okay. Okay. So the constraint is to make sure that we get an upper bound for the objective function. Okay, so we want to make sure that when we compute the weighted combination, the coefficient of x1 is at least 1, and the coefficient of x2 is at least 1, and so on and so forth. So we can actually first write down the right-hand side of these constraints. Okay, so the right-hand side of these constraints are just the coefficients of the variables in the objective function in the original problem. Okay. Okay, so coefficient of x1. Okay. So let's highlight x1 in the constraints. Okay. So x1 appears in the first and the fourth. Okay. So these are the two constraints where x1 appears. So what's the coefficient in the weighted combination? It's just y1 plus y4. Okay, y1 plus y4. Okay. And observe that this is the first constraint, and it happens to be the two endpoints of the first edge, E1. Okay. Okay. Now x2. Okay. So x2 appears here and here. Okay. y1 and y5. So the coefficient is just y1 plus y5. Okay. So y1 and y5. Okay. So it happens to be the endpoints of E2. Okay. And now we're considering the second constraint. Okay, so next, the coefficient of x3. So the coefficient of x3 in a weighted combination is y2 plus y4. Okay, so y2 and y4. Okay, so these are the endpoints of the third edge. Okay, so next x4. Okay, so x4 here and here. Okay, so y2 plus y6. Okay, or y2 plus y6. Okay, so it's the fourth edge, and this is the fourth constraint. So I think you can see the pattern here. Okay, so we create a constraint basically for every edge. Okay, and the left-hand side of the constraint is just the sum of the variables correspond to the two endpoints. Okay. All right, so next x5. Okay, so the coefficient of x5 is y3 plus y4. Oh, sorry. Okay, so y3, y4. Okay, so these are the two endpoints of the fifth edge. Okay, so next x6, sorry. So it's y3 plus y5, okay? So y3, y5, so it's the endpoints of E6. And finally, x7. Okay, so y3 plus y6. Okay. Okay. And make sure that all the dual variables, they cannot be negative. Okay, so this is your dual problem. So we get this dual problem by applying this primordial transformation. So this is a very systematic transformation. You don't have to understand the difficulty of the problem of the graph structure, no. All you have to do is to list the constraints, and then you can get this dual problem, okay? And now, we have this dual problem, okay? But this is not the end of the story, okay? So I want to find out the physical meaning of this dual problem, okay? So what is the physical meaning of this problem? So first of all, we have variables corresponds to every vertex, okay? And since these are variables, I think it's natural to interpret these variables as binary, as whether this vertex is chosen or not, okay? So if it's 0, this means Vi is chosen. And, is not chosen. So this is a very common trick, okay? Whenever you want to pick some elements from a universe, you'll create a variable, a binary variable for every element. So whenever it's 1, it says it should be chosen. If it's 0, it means it's not chosen, okay? So this is a pretty standard way, okay? Now we have to look at the objective function, okay? So the objective function says we want to minimize the sum of the variables. Now because these variables indicating whether they are chosen or not, so this basically says I want to choose the smallest number of vertices. I want to choose the least possible vertices, okay? So minimize the number of chosen vertices, okay? So that's the physical meaning when you have this binary variable and this interpretation. So the goal is to choose the smallest possible number of vertices. Okay, now the constraint, okay? So we know that we have a constraint for every variable in a primal problem. And the variable in a primal problem, it's like it's corresponding to the age, okay? So we have, in the dual problem, we have a constraint for every age, okay? So for example, y1, y4, okay? y1, y4, okay? So this corresponds to the first age, okay, E1. And the second constraint, y1, y5, y1, y5, these two correspond to E2, okay? So we have a constraint for every age. And the two variables are just the endpoints, okay? So because we have this definition, so basically the left-hand side is just the number of endpoints that you choose from that edge, okay? So y1 plus y4, this is the number of endpoints that you choose for E1, okay? So y1 plus y5, okay? So this is the number of endpoints of E2 that gets chosen, okay? Okay. And the right-hand side is easy, okay? It's at least 1. So this means for every age, you have to choose at least one endpoint, okay? So for example, for E7, we have to choose at least one endpoint. Okay? So for every age, we have to choose at least one endpoint. And we want to minimize the number of chosen endpoints. So that's the dual problem. Okay? And I think we all know that this is just the vertex cover problem, okay? Where we say that we cover an edge by choosing endpoints, okay? Okay, so this is how we get vertex cover from matching, okay? By applying this primordial transformation. 有问题吗？所以基本上，我们之前说那些 matching 跟 vertex cover， 还有 independent set 跟 edge cover， 它们的关系就是从这样子的转换得到的。所以它事实上不是有一个很天才或突然间灵光乍现，不是 ，OK？ 事实上是有一个很有系统化、很有制度的方式，可以得到对应的问题。OK？ 有问题吗？OK， 如果没有问题，因为时间也差不多，我们先下课，然后我们等一下来看 maximize independent set，OK，、然后看它怎么转成 edge cover。所以我们先下课。 All right, so next, let's consider maxima independent set, okay? So I think this whole process, it serves two purposes, okay? So the first one is to give you some experience to model this graph theory problem into mathematical or integer linear program, okay? By the way, so these problems, these are called integer or linear program, okay? So you can see that all the variables, they must take integer values. And we have linear constraints, okay? So we don't have quadratic or like log or square root, things like that. So every constraint, every objective function is linear, okay? All right, so the first purpose is to model this graph theory problem into integer or linear program, okay? So that's the first purpose. And the second purpose is to perform this problem transformation, okay? So whenever you have some problem, perhaps it's difficult to tackle, then you can apply this problem transformation to see whether there are some clues, okay? So in fact, there are some algorithms, okay, that are designed based on this primordial transformation, okay? But I won't cover those parts in this course, okay? Okay, so back to maximum independent set, okay? So whenever you want to model a problem as an integer or linear program, first you have to create the variables, okay? And usually the variables is usually the easiest part, okay? So normally it would be a binary variable indicating whether it's chosen or not, okay? So for maximum independent set, the problem is to pick vertices, okay? And you want to pick vertices so that the chosen vertices that do not, that they are not adjacent to each other, okay? And you want to maximize the number of vertices that you choose. So naturally, you will create a variable for every vertex because that's the thing that you have to decide, whether V1 is chosen or not, whether V2 is chosen or not, and so on and so forth. So create a variable for every vertex, okay? So IS stands for independent set, okay? Yeah, so that's the variable, okay? So we have 6 vertices, therefore we have 6 variables. Okay, then we have to figure out the objective function, so the goal, okay? Because this is maximum independent set, so this is a maximization problem, okay? So max something, okay? Max the objective function. And what's the objective function? So the objective function or the goal is to maximize the number of vertices that you choose, okay? So pretty similar to the idea we had for matching. So for matching, you want to maximize the number of chosen edges. And for independent set, we want to maximize the number of chosen vertices, okay? Okay, so this is your objective function, okay? The goal. Okay, so the last part to formulating this integer or linear program is to list the constraint, okay? So for maximum independent set, the constraint is that for any 2 chosen vertices, they cannot be adjacent to each other, okay? So to formulate this as an inequality, linear inequality, we can consider each edge, okay? So for example, E1, okay? When we consider E1, we know that we cannot choose both V1 and V4. In other words, among V1 and V4, we can choose at most one of them, okay? So for E1, we can have a constraint like x1 plus x4 is at most 1, okay? So this makes sure that at most V1 or V4, at most one of them is chosen, okay? So this is for E1, and we can list all the constraints for other edges, okay? So x1 plus x5, so this is for E2, okay? And for E3, it's x2 plus x4. And for E4, it's x2 plus x6. And for E5, it's x3 plus x4. Okay. So for every edge, there's a corresponding constraint saying that you cannot choose both endpoints, okay? Because it's an independent set. But I think yeah, okay. Okay, so let's independent set. And next, let's find a dual problem, okay? Okay, so the dual problem is a minimization problem, and the first step is always to create dual variables. Okay? And recall that in the primal problem, we have a constant for every age. So this means we have a dual variable for every age. Okay? Okay? So this time, I write the dual variables alongside the ages. Okay, second step, we have to figure out the objective function. Okay. So the objective function is just, again, like the product of these two columns. Okay. Because we want to find a weighted combination. Okay. And for the right-hand side, it's just the right-hand side times the dual variable. And we just need to figure out the sum. And the sum here is easy, okay? So it's just the sum of all the variables. Okay? Okay, so the last part is to figure out the coefficient. Okay? So first of all, the coefficient of x1, x2, up to x6, you can see that all the coefficient here is 1. So this means in a dual problem, the constraint always has this form, okay? It's at least 1, okay? So these are the right-hand side of the constraint, which corresponds to the coefficient in the objective function. Because we want to have an upper bound. Okay. Okay. Okay, so x1. So let's see what's the coefficient of x1. Okay, so x1 appears in the first two constraints, okay, corresponding to y1 and y2. Okay? So y1 plus y2 is at least 1, okay? So that's x1. And for x2, it appears in the third and fourth constraint. So y3 plus y4, okay? So y3 and y4, so it corresponds to E3 and E4, which happen to be the edges incident to V2, okay? So, okay, so next x3. Okay, so x3 appears in the last three constraints. So y5, y6, and y7. Okay, so these three edges. Okay, which are the edges incident to V3. Okay, so next, x4. Okay. So x4 appears in the first, third, and fifth. Okay, first, third, and fifth. Okay, so these are the edges incident to V5 or V4. Okay, so I think the pattern is clear. Okay, so we have for every vertex a constraint in the dual problem. Okay, and a constraint basically says the sum of the dual variable incident to it. The sum should be at least 1. Okay. So following this pattern, the next constraint should be y2 plus y6. Okay. So let's check. Okay. So x5. Okay. So it appears in second and sixth constraint. So last x6, so y4 plus y7. Okay. y4, this h, and y7. Okay, so this is the dual problem. Okay. Okay, so in the first step, we create the primal problem in the form of linear integer program, and in the second step, we create the dual problem, and the third step, which I think is the most important step, is to figure out the physical meaning of the dual problem. Okay, so once again, you can always try to view these variables as binary variable. Okay. And because we have variables corresponding to ages, so it's like for every age, we have to determine whether it is chosen or not. Okay, so it's a problem of choosing ages. Okay, and then we look at the constraint. Oh, sorry. Let's first look at the objective function. Okay, so the objective function is to minimize all the variables, the sum. Okay. So it means we want to choose the minimum number of edges. Okay, so I want to minimize the chosen edges. So that's the physical meaning. Okay. Okay. And for the constraint, because we have a constraint for every vertex, right? Because the constraint are corresponding to the vertices and the variables here which correspond to the vertices. So we have a constraint for every vertex, okay? And I think it's quite easy to observe that the constraint says for every instant edges, we have to pick at least one of them, okay? So for example, let's look at, this is, so this is the fourth constraint, okay? So we look at V4, okay? And the constraint says y1 plus y3 plus y5, y1, y3, and y5. So this corresponds to the edges incident to V4, okay? And it should be at least 1, which means we have to choose at least one of them, okay? All right, so with this interpretation, we get the edge cover problem because edge cover is to find a set of edges, and you want to find the smallest edge cover. And this edge cover should cover every vertex, okay? So to cover every vertex, this means for every vertex, we should choose at least one of its instant edges, okay? So that's how we get the edge cover problem. OK， 所以有问题吗？所以刚刚这边是把maximum independent set， 然后我们先把 maximum independent set 把它用就是 integer 或 linear program 列出来之后，我们把它的 dual problem 也找出来，然后最后就是我们把这些 dual problem 的变数啦，或目标或限制是赋予它们一些物理意义，然后最后我们就可以得到 H cover。OK。有问题吗？Okay, so if not, I'm going to give you like the general form of primordial transformation. Okay. Okay, so in general, usually we use n to denote the number of variables, and m is the number of constraints. Okay, so this means we have x1, x2, x3 up to xn. Okay. Okay, so let's first assume that the primal problem is a maximization problem, okay? And the coefficient is just C1, C2 up to Cn, okay? So, yeah. Okay, so this is our objective function, okay? So it's just a weighted combination of the variables, okay? So this C1, C2, these are constants, okay? These are not variables. Okay, and then we have the constraint, okay? So starting from the first one, so usually we use A, is lowercase a to denote the coefficient in the constraint. Okay, so this is the left-hand side, which is just another weighted combination, okay? And because this is a maximization problem, okay, So it makes sense to have some upper bound, okay? Otherwise, you can just, for example, set x1 to infinity, x2 to infinity, to maximize this. So naturally, we have some upper bound for maximization problem. Okay, and we use B to denote the right-hand side. Okay, so this is your first constraint, and the second constraint. Okay, so this is your second constraint. The third one. Okay, so because we have m constraint, so the last one is am1x1 plus am2x2 up to amnxn is less than or equal to bm. Okay. So this is a general form of primal problem. Okay. And all the variables are non-negative. So this is a very general representation that can capture many different problems. Okay. Perhaps you may be wondering, what if some of the variables for my problem can take a negative value? Okay. For example, it can be like -2. Okay. So it seems like it does not fit into this model. But actually, by doing some transformation, you can actually transform the problem you have into this form. Okay? So I want to say is that this form is very general. Okay? Okay, and by the way, this CI, AIJ, BI, these are constants, okay? So these are not variables. Okay, so for the dual problem, it's a minimization problem, okay? And we have variables, dual variables, y1, y2 up to ym, okay? And what's the objective function? It's just the right-hand side, and the product of the right-hand side and the dual problem, and the dual variables. So it's b1, y1 plus b2, y2 up to bm, ym. Okay? So that's the objective function. And then the constraint, okay? So let's first write down the right-hand side of the constraint, okay? So the purpose of the constraint is to make sure that the weighted combination is an upper bound for the objective function here. So we have to make sure that the coefficient of x1 is at least c1. And the coefficient of x2 is at least c2. Okay? So these are the right-hand side of the constraints. Okay? Now for the left-hand side, it's just the coefficient of x1 in the weighted combination. So you have to figure out what's the coefficient of x1 when you multiply b1 into the left-hand side, b2 into the left-hand side, and so on and so forth. So what you get is the coefficient of x1 is a11 y1, okay? So this is a11 y1, and then you have a21 y2, a31 y3, okay? And the last term is am1 ym. Okay? So this is the coefficient of x1 for the weighted combination. Okay? And I want to make sure that this coefficient is at this C1, so that the weighted combination is an upper bound. Okay? So that's x1. And for x2, the idea is similar. Okay? So this time it's a1, 2. So let me perhaps highlight this row. So a12 y1 plus a22 y2. Okay. Okay, the third one. Okay. Okay, so the last one. Okay, so this is the coefficient of xn. Okay. Okay, and finally, all the dual variables are non-negative. Okay. So this is the dual problem. Okay. Okay, so if you Google primordial dual transformation, probably you're going to see some more compact representation like this. So we have a vector C, so this is just C1, C2 up to Cn. We have the vector B, and we have the variable So there's a compact way of representing primal and dual problems. So first of all, observe that this C1, X1, C2, X2, the sum is just like the product of these two, okay? These two vectors. Okay, so if you use inner product to represent this product, then this becomes C transpose X, okay? And the constraint, well, the right-hand side, the left-hand side is just this matrix times X, okay? And this is MSB. And this vector, so every element in this vector is at this 0. So this is like, this is not a number. This is a vector consisting of zeros, okay? So this is the primal problem. And the dual problem, so this is a minimization problem. And what's the objective function? This is like the product of B and Y, okay? But to take the inner product, we have to first transpose B. Okay? So it's B transpose Y. And the constraint is like we transpose this whole matrix A, okay? So you can see that originally this is like a vertical column, then when you get to the dual problem, this becomes a horizontal row. So vertex becomes, columns becomes row. Okay, and this is at least C. Okay. Okay. But I don't think you have to like memorize this, because the really important idea is to know that all this transformation, it's just to find a proper weighted combination, okay? So I think that's the key idea. 好，所以这边我刚刚只是把，比如说如果你去 Google， 如果你去找一些书的话，你可能会看到这样的形式，那甚至你可能会看到这种更简洁的表示的方法，但其实他们要讲的东西是一样的 ，OK？ 那关键就是我们要找到好的那种权重的组合，然后可以让你找到 upper bound，OK？ 好，所以这里有问题吗？坦白讲，这边没有什么新的东西，只是确保你们如果有去找资料的话，确保说你们找的东西跟我们上课讲的是一样。Okay, so before we end today's discussion, I want to make a small remark. Okay. So in our previous discussion, the primal problem is always a maximization problem, okay? And then the dual problem is always a minimization problem. But for some application, the problem that we're considering is a minimization problem, not a maximization problem, okay? So in fact, the primal problem can also be a minimization problem, okay? So for example, suppose your problem is to find the minimum vertex cover, right? So this is your primal problem, the vertex cover problem. And you have a solution, okay? And you want to see whether this solution is the best, okay? So in this case, instead of finding upper bound, right, because vertex cover is a minimization problem, so you want to find a lower bound, okay? So the result, the takeaway is that I can actually make this the primal problem, then the dual problem will be this, okay? So this is when primal problem is a minimization problem. Okay. Okay, I think I can give you a quick example showing that the same idea works even if the primal problem is a minimization problem. Okay. So let's treat this minimization problem as the primal problem, okay? Okay, so this is your primal problem. Still, the idea is to find weighted combination, but this time I want to make sure that the weighted combination is a lower bound, okay? Because this is a minimization problem, okay? So for example, let's try some solution. I think you can try like set y1 to 1, okay, like this, okay? 1, 6, 0, okay? I think this will give you 2,000, okay? So yeah, this is a decent solution, but I want to find a better solution. So this time I can try, for example, this time I make y3 1 and y1 0. Okay? And according to the second constraint, this is, no, sorry, okay? So we only have two constraints, okay? So because now y3 is 1, so y2 is at most 5. Okay, so this gives 1900, okay? So we get a better solution because this is a minimization problem, okay? All right, so at this point, you can try other possible solutions, but well, you're never going to find a better solution. So we want to have a proof, okay? Once again, the idea is to apply this weighted combination, okay? So we can try okay, so for example, let's try, we multiply the first constant by 200, okay? And the second constant by 400. Okay. So the result is okay. Now, the weighted combination gives us 200y1 plus 400y2 plus 600y3. Is it a valid lower bound? Because now we want to find lower bound instead of upper bound. OK， 所以我们现在跟刚刚不一样的事情，我们刚刚都要找上限，然后我们现在要找下限。OK， 所以本来的系数是200、300、400，那现在呢，我们把它变成这样子。OK， 所以这边200、400、600。所以我要说的是，像这样子，它就不是一个 lower bound。OK， 因为这里的系数都太大，我们要确保的是我们系数都要比较小。OK， 系数不能超过200、300、400。OK， 所以或许我们应该调整一下。So 400 for x2, for the second constant is too large, all right? So you can reduce it to 200, okay? Okay, so now this is a valid lower bound, okay, because we get 200 y1, okay, and 200 y2, which is less than 300 y2, so that's okay, and 400 y3, this matches 400 y3, okay. So we have a lower bound, 1400, okay. So not exactly equal to 1900. So we have to find a better lower bound. By better, I mean a larger lower bound, okay? So you see that for this dual problem, we want to maximize the right-hand side instead of minimize the right-hand side, okay? So let's try to find a better upper bound, a lower bound, sorry. I think we can do like this, okay? So the weight for the first constraint is 100, and the weight for the second constraint is 300. So the weighted combination okay, so this time it becomes 100 Y1, 300 Y2, 400 Y3, and this is at least 1900, okay? So two observations. So first, now this right-hand side equals our solution. So that's first. And second is that you can see that in this weighted combination, actually the coefficient of Y1 is strictly less than the coefficient in the primal problem. So this is why in the dual problem, we don't say that this is equal, okay? Because sometimes it's impossible to find dual variables so that in the weighted combination, the coefficient is exactly equal to the coefficient in the primal problem. Sometimes it's not feasible. But that's okay, because all we have to find is to find some bound, okay? So for this problem, all we have to do is to find some lower bound, okay? So it's okay if the coefficient of Y1, oh, not this one. So it's okay if the coefficient of Y1 is less than that in the primal problem. That's okay, because all we have to find is a lower bound, okay? Right, so I think hopefully you can see that the idea still applies to minimization problem. It's just that we have to change the idea of finding the smallest upper bound to finding the largest lower bound, okay? So when the primal problem is a minimization problem, the dual problem becomes a maximization problem, okay? Yeah, I think that's it, okay? So yeah, so next week we're going to have some paper presentation, and if there are some time remaining, I can discuss more information about primordial transformation, okay? So let's call it a day.